All right, so continuing with where we left off, area of a surface of revolution is the next topic. So let's get to it. The polar coordinate version of the formulas are very much like the parametric versions that we already did. So I'm going to just go ahead and give you those formulas. The surface area is going to be found by multiplying 2 pi times a radius function, and that can be one of two things. So let me do the first one. Sorry, alpha, not a. Alpha to beta of our radius. And what we're going to have to do is realize that there are two things we could rotate about, generally speaking. One is the polar axis. So if we have a curve like this and revolve it about the polar axis, kind of like the x-axis, then our radius that we're measuring is the distance from the axis of revolution to the curve. That's our radius of our solid that we form, whose surface area we're finding. And that radius is going to be r, or the function of theta. Oh, I'm sorry. Let me back up. I said something wrong. Let me just back up a bit. So that is a measure of y, right? I'm sorry, r would have been from the pole to there, which is not what we're talking about. So I apologize for that mistake. It's not r. So ignore the r that I wrote there. The distance from the x-axis to the curve is y. And remember, y is r sine theta. And so r would be, the letter r that we normally use, or it could be written as f of theta, which is what they do in the formula. So f of theta sine of theta. So that's just like what we saw before. This is 2 pi r, where the radius of revolution isn't the r from the formula, but rather the radius of the solid that's being created, and the radius of that solid is y, and y is r sine theta. Okay, multiplied by the square root of the same thing we used with the arc length. That's f of theta squared plus f prime of theta quantity squared d theta. Sorry, that's running into my other picture that I had there. All right. Then the other major axis of revolution is what we would think of as the y-axis. And so let me draw this picture way over here. And if we have our curve and we want to measure from the axis of revolution, which is the line theta equals pi over 2, that's what the y-axis is called, the positive, well, yeah, the entire line, the y-axis is theta equals pi over 2. If we're revolving about that, then the radius of the solid that we're creating is measured from the y-axis to the curve, which is a measure of x. And if you'll recall, x is r cosine theta. And in this formula for r, we're going to avoid confusion, we're using f of theta to make really sure everybody knows what's what. All right, so that formula would be from alpha to beta, f of theta cosine theta, then times the square root that we've seen before, f of theta quantity squared plus f prime of theta quantity squared d theta. Kind of separate that and kind of try to separate that. So those are the two formulas. That depends on whether we're revolving about the polar axis or the line theta equals pi over 2, which you might think of as the y-axis. Okay, so our example here is find the area of the surface formed by revolving the circle r equals f of theta equals cosine theta about the line theta equals pi over 2. So we've got the graph of that, of course, is a circle with one point on the pole. Since it's r equals 1 cosine theta, the diameter is 1 and the center is on the x-axis. So here's where 1 is, and we have a circle that looks like this. And we're revolving that circle about the line theta equals pi over 2, aka the y-axis. So that means we're using the second formula that I went through just a moment ago, because we're revolving about that axis. And so we'll have 2 pi for the surface area, 2 pi times. We're going to have to figure out what created that circle. And you got to be really careful here, because we're used to thinking of regular cosine as having a period of 2 pi. And in graphing some of these, you're actually having to do more than 0 to 2 pi to get the full graph, sometimes a lot less. And so you're going to have to actually think through what created that graph. We haven't talked about that much, so I think this is a good time to talk about it and why we need to know, well, what angles create a single circle? Because if you go too far, you'll be revolving 2 separate things, or 3 separate things, or half of a thing, if you don't go far enough, instead of one single circle revolved about that. So you got to be really, really cognizant of how you got this. So let's think through some values, and I kind of hate to make a table of values too often, but I think in this case it's actually going to help us. So when theta is 0, of course cosine of 0 is 1. When theta is pi over 2, cosine of pi over 2 is 0. And from 0 to pi over 2, we will have gone through all of these places. I don't know if you can see those. I'm going to make the dots a little bit more evident. We're going to be going through all of those dots from 0 to pi over 2. That's half the circle already. So if I then go to pi, whoops, let me change colors back. If I then go to pi, cosine of pi is -1. And so at the angle pi, which is over here, we're at -1, so we go the other way along the opposite way of the line, and that puts us at this point right here. It gets us all the way back. So from pi over 2 to pi, it actually goes through these points, completing the circle one time. And what happens in the second and third quadrant angles, you're getting negative answers, which is throwing the graph from the second quadrant with a positive r into the fourth quadrant. And likewise, I'm sorry, we just did the second quadrant, which gave us those points, right? The third quadrant would flip those answers into the first quadrant. We get those again. And when we use fourth quadrant angles, we'd be getting those same places again with positive r values. So we'd actually go around this circle twice if we went from 0 to 2 pi. So you do have to know this in order to get the bounds right. We complete one circle going from 0 to pi. Okay, so our f of theta, of course, is cosine theta. So cosine theta times the other cosine theta. Okay, so I've got f of theta once, and then another cosine theta times those two multiplied together give us cosine theta, times the square root of cosine of theta squared plus, then we need to find the derivative, f prime of theta. The derivative of cosine theta is negative sine of theta. So that will be negative sine of theta, quantity squared, d theta. Now I do want you to realize that sometimes on a testing situation I'll ask you set up but do not evaluate. So if I ask you to set it up and do not evaluate, you could actually stop right here. You don't have to do any simplification. I'm happy with that. If, however, I say I want you to go on and kind of show me that you still know how to integrate and do all those pre-calculus and calculus things that would lead you to an answer, then you need to do this. So let's go ahead and do this one so we can see if we can actually accomplish this. So cosine times cosine will make that cosine squared theta. That will be cosine squared theta plus, and then negative sine theta times negative sine theta is positive sine squared theta. And luckily we know that Pythagorean identity that says that sine squared theta plus cosine squared theta is equal to 1. So this right here will become 1, and the square root of 1 is 1, and so it simplifies to be 2 pi times the integral from 0 to pi of just plain old cosine squared theta. Then the integral of that will involve using the trig identity, the power reducing identity for cosine. So if you'll recall, that's 1 plus cosine of twice the angle of the squared version of this, so twice theta over 2 d theta. Okay, so if I take that constant 2 that's in the denominator out in front as a 1/2, 2 pi times 1/2 will be pi. And so we're left to integrate 1 plus cosine of 2 theta d theta. All right, so the antiderivative of 1 is theta plus the antiderivative of cosine of kx is 1 over k, so 1 over 2 sine of kx, and that will be evaluated from 0 to pi. We'll start by substituting in pi first, minus substituting in 0. So that'll be pi times pi plus 1/2 sine of 2 times pi, so 2 pi, minus pi times 0 plus 1/2 sine of 2 times 0. Of course, 2 times 0 is 0. And simplifying this, let's start at the end. Sine of 0 is 0, so 0 plus 1/2 times 0 is 0. So that whole ending part is 0, and we didn't just ignore that. So distributing the pi, we get pi squared plus 1/2 times the pi we're distributing times the sine of 2 pi, excuse me. And the sine of 2 pi is 0. And so our final answer is pi squared. All right, so that completes this section, and I will turn this off and see you in class.